more elastic collision or more collisions, and this is our elastic example, and it's tough. It's not tough, it's just painful, algebraically painful. So let's look at it. We have a super ball, which is my first hint that it's elastic, by the way, just because if ever I say super ball, that's what I mean. We know its mass, it rolls along, it bumps into another one head on. So again, no angles. As soon as you see angles, the whole problem changes, by the way. And which tells us it's an elastic collision. Okay, so it will. If you're supposed to treat it as elastic, that information will be given to you. Maybe the only other way I could word it would be with no energy lost, and that would mean elastic, and you have to interpret it that. Anyways, it's asking for the speed of each. So it's asking us for two things, right? So we know two things. We know four things because we know two masses and two initial speeds or velocities right here, and we don't know anything afterwards besides the masses. Okay, so we need to solve two equations, two unknowns. So just a little thing I always do when dealing with elastic ones, and you don't have to do this, but I say let big A be VA2 and big B be VB2, just because you want to write all the subscripts and it gets confusing looking. Okay, so I just do this because we're going to solve for A and B, right? And just to make the numbers look a bit nicer. So looking at my first equation then, I've got my, here we go, I'm calling the big one A and the little one B. So it's got MA is 2, VA1 is 2.3, and then the initial momentum of this one is 0, right? Because 1 times 0 is 0. And that's going to be equal to 2 times what I'm looking for, A, plus 1 times B, or just B, right? So here's my first equation. And what I did in this step is rearranged it to get B by itself because I will be substituting that in, right? I'm going to use substitution to do this, to solve for B and A. Because here's two equations, two unknowns. That tells you you're going to have to use elimination or substitution. I guess theoretically you could use graphing too, couldn't you? But we're not going to. We're going to use substitution, okay? So you take the conservation of momentum, you isolate one of the variables you're looking for, and that's equation 1. Again, I just did this to make it look prettier. I didn't want to deal with subscripts anymore. Okay, now I have a second equation when I deal with an elastic collision, and that's energy. So take the same things. Here's the equation. Again, the initial energy of B is 0 because VB is 0, right? VB1 is 0. So I take 2 times the initial speed. By the way, little food for thought. If they were moving towards each other, this would be a negative sign right here. But in the energy, it would still be a plus because it's speed. I didn't do that in this example, but that might be something important to know. That this would be negative if they were moving in opposite directions towards each other because the vector of velocity. But with energy, you deal with speed, so then you're just looking at magnitudes. So it would be plus. Anyway, just substituting in. So now I have 2 times A squared, right? Plus 1 times B squared. So great. Now I have a second equation. So what I'm going to do is substitute equation 1 into equation 2. So instead of writing B, here comes the algebraic fun. With B, instead of writing B, I'm going to write this, 4.6 minus 2A, because I figured out using momentum that was the relationship, right? So now all the fun begins. So this part's just 10.58, 2A squared, that's easy. Now, I have to square all this. So 4.6 squared minus 2 times 4.6 times 2 for this one, right? I'm just doing A minus B squared, right? If you don't remember how I came up with this line right here, just ask me in class. You will have to do this on your own, so you should make sure you understand the algebraic steps, okay? So getting from here to here, if you don't get that, it's just using the fact that A minus B squared equals A squared minus 2AB plus B squared, okay? That's how I came up with this line right here. And then all I'm doing now is just trying to solve for A, which it's ugly, but I'm gonna try to. It's gonna turn into a quadratic, right? So to use a quadratic formula, I have to get everything equal to 0. So I bring everything over to the other side. So I subtract the 2a squared. Actually, no, I brought the 10.58 over here. See that? So I went 6a squared, which is 2 plus 4, minus 18.4 times a. Then I have this, and I subtract 10.58. Okay, so I sub that into the quad solver. Whether you have one in your calculator or whether you want to go on the internet and go quad solver, I could do that too. Come on, quad solver. Math is fun. Look at that. It is fun. We can solve it for you. Okay. So let's sub in our numbers then. What's our A and our B and our C? Our A is 6 and our B is negative 18.4. And our C is 10.58. Okay, there's my end formula, so 10.58. And I get two answers, 2.3 and 0.67, right? Or 7.6, sorry, 7.7, I guess. So there's my two answers. So, you know you did it right up to this point if one of the answers you got was the initial speed. Okay, I'm solving for A. My initial speed of A is 2.3. At the end, after I use the quadratic solver, if I get 2.3, then I know I did it right. Okay? So here, and then but the thing is that you don't choose that one. Oops, I just want to turn that on. You don't choose that one, you choose the other. Okay? So 0.77 then is my answer. It could be that A turned out to be negative. A could turn out to be negative, and that would be fine. Okay? You just sub it in here, you get your A, because that just means that A turned around and went the other direction, which sometimes happens. Okay? So there's my two answers, and let's just see if they make sense. Okay? Let's scroll up, look at the top, and say, okay, A ends up at 0.77 meters per second. And they're both positive, by the way. And B ends up being faster. Well, it's hard to say what makes sense in a situation like this when you don't know either final velocity, but it does make sense. I know that this one is right. A was right because it could have been 2.3 or 0.77, so I know my quadratic worked out fine and we did everything right. So given that that is 0.77, does it make sense that that is as fast as 3.1? For B is 3.1. And the reason I say it does is you're looking at a total momentum. So this is a big mass, right? A big mass and a medium speed. That big mass ends up going quite a bit slower afterwards. So that momentum had to be given to this ball, right? And this ball then, its momentum, it's got a small mass, so it's going to have a bigger, even a bigger speed. So, I mean, within reason, it makes sense, right? So I'm going to check mark that and say, good work. Good work to us, because that was really hard and a lot of work. Wait till you do it on your own.